Hello, y'all. Welcome to lesson 77 on my DP chemistry curriculum. Today we're doing reactivity 1.4.1. It's an HL topic. So this is about entropy, S, which is a measure of the dispersal or distribution of matter and or energy in a system. The more ways energy can be distributed, the higher the entropy. Under the same conditions, the entropy of a gas is greater than that of a liquid, which is greater than that of a solid. Predict whether physical chemical change will have an increase or decrease of entropy, and then calculate standard entropy changes from standard entropy values. So it seems like a lot, but let's break it down from the start. So entropy, S, is basically a measure of randomness, or like distribution of particles. So another way of thinking about it is chaos. An increased entropy is an increase towards chaos. You can kind of think about it too because it always increases or tends to increase. That if you look at your room that you live in, your bedroom or whatever, it gets messy on its own. Particles start going everywhere, dead skin cells fall off. Just naturally, the room will get messier. And to actually clean it, you have to put energy in. So to go against entropy, you have to add energy. But in general, entropy or chaos or randomness or the distribution of particles tends to increase. So generally you refer to it as like high entropy generally refers to spread out particles and vice versa, actually. So that's kind of how we envision it. Much like what we said with matter in the intro, solid, liquid, gas, as we move this way, we have an increase in entropy. So we're going to first start by talking about changes in entropy in physical systems. So we'll start out with changes of entropy, which is going to be denoted as delta S because delta always refers to change. And we're going to start out with physical systems. So that includes things like state changes. So like melting spreads them out, that would be an increase or positive delta S. Meanwhile, freezing, the opposite, is a decrease in entropy, negative delta S. And we can apply this to all the phase changes, sublimation, deposition, condensation, vaporization. It's the same thing. As we move towards gases, we have an increase in entropy, and as we move towards liquids and solids, we decrease in entropy. But other physical changes can also exist. So, for example, maybe we have dissolution or dissolving. Once again, the particles are spreading out. So, like, for example, we could take sodium chloride in its solid state and then we dissolve it in water, becoming sodium positive ions, aqueous, plus chloride negative ions, aqueous. Not only have we increased the number of particles, we've gone from 1 mole of particles to 2 mole of particles. They've spread out and they're in an aqueous state. In this case, this would also be a positive delta S, an increase in entropy, an increase in randomness. So you can generally use this to understand the change in entropy in a reaction. Maybe not yet calculate it, but at least determine whether that reaction is going to increase or decrease in entropy overall. In addition to physical processes, we can also look at chemical processes or chemical reactions. And we can predict entropy change in chemical reactions too. And generally what we're looking is at moles. So we're looking for changes in moles or mole ratio, as well as changes in state. So the same thing may not be in the products and reactants, but we may have different states. So let's take the decomposition of hydrogen peroxide, H2O2 liquid, or actually this would be in water, so this would probably be aqueous. And as that decomposes, we get H2O liquid plus O2 gas, and we'll balance that out real quick. Now we go from 2 moles of reactant to 2 moles of liquid product plus 1 mole of gaseous product. So this shows that not only do we have more moles in products, more mole in product, but we also have a higher entropy state, higher entropy state being the oxygen gas. So in this case, we can predict that there will be a positive delta S. Now, the reverse reaction, of course, would therefore be negative. Now, we could do a negative one as well, but I'd rather look at a weird case here. If we take hydrogen gas and react it with chlorine gas, 1 mole plus 1 mole, we make 2 moles of hydrochloric acid gas. Now, in this case, what is the change in entropy? We have 1 mole gas, 1 mole gas, and now we have 2 mole gas. So as we look at this reaction, we still have the same moles on either side, same amount, and in addition to that, they're both in their gaseous state. So in this case, we would actually say that there is either a minimal, or we might even say unknown, entropy change. So sometimes we can't predict it. We're going to have to calculate it instead. So sometimes it's unpredictable based on just observations of state changes and amount of moles on products and reactant sides. So how do we actually go ahead and calculate it? How can we know for sure? That's going to be the next section. This is where we introduce standard entropy values. Once again, when we're talking about standard values, we're going to use that symbol, but it'll be appended to our entropy symbol. Furthermore, in addition to standard entropy values, we'll also talk about standard changes in entropy. And again, that delta means change. So how do we do this one? Well, first off, what the heck is standard entropy? And that's the entropy change of 1 mole of substance. It's always 1 mole for a standard value. 1 mole of substance heated from, just a moment, absolute zero or 0 Kelvin all the way to 298 Kelvin or approximate room temperature, 25 Celsius. Because this is an increase in kinetic energy, we know that these values are going to be always positive. So we're always going to have positive standard entropy values. Furthermore, we can calculate the delta S standard from standard entropy values of a reaction. So instead of predicting all the time, we can just calculate it. We can use the equation that's within your data booklet. Delta S standard is equal to the sum of the entropy value standard of your reactants minus the sum, oops, of the entropy values of the products. Or sorry, I reversed that. Products minus reactants. Whoops, 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 whoops. Just going ahead and products minus reactants. Because when we have more entropy in the products, we're going to be doing a increase in entropy versus a decrease. So we want our equation to reflect that. So first, one thing before we move forward, where do we get these values? Well, you can just turn to section 13 of your data booklet. until they adapt the data booklet. But for now, they're in section 13. And we can go ahead and do some practice problems. So let's take a look at maybe C4H8 butene reacting with water, H2O. We'll need state symbols in there as that is very important to our entropy. And when we react these two, we can get butanol, C4H9OH, and that will be in the liquid state. If we look at section 13 for our data booklet, we can find that butene is going to have an entropy value of about 310 joules Kelvin inverse mole inverse. So 310 joules per Kelvin per mole. Water in the gaseous state is going to have a value of 189 joules Kelvin inverse mole inverse. And butanol is going to have a value of 228 joules Kelvin inverse mole inverse. Before we actually calculate this, though, let's take a quick moment to predict which way our entropy is going to go. You can pause it and try and predict it, but I'm going to go over it right now. So we have 1 mole of liquid and 1 mole of liquid. So those are going to have approximately the same entropy values. However, we also have a mole of gas. So we're going from 2 moles of reactant to 1 mole of product, and we're going from a high energy state of matter like gas to a lower energy state of matter like liquid. So I'm going to predict a decrease in entropy. As we plug our values into the equation, we find that delta S standard is going to be approximately 228, or not approximately, exactly, minus the sum of 310 plus 189. Plugging these into my calculator, and I get a value of negative 271 joules Kelvin inverse mole inverse. So our change was correct. Our prediction was correct. We expected a decrease in entropy, and we got a decrease in entropy. This is all there really is for standard entropy values. Once we start talking about spontaneous reactions, what's known as Gibbs energy and spontaneous changes are in our next video. We'll start using this a little more. But for now, that's it. I hope this helps and have a great day.